Next, we are going to discuss distance relays. So these are majorly used in the protection of transmission lines. So what happens is, these relays operate only when the fault is within a certain distance from the relay. Okay, so that means if you have a transmission line, let us say like this, and you have a relay here. Okay, this is the CT which is fed to the relay. Now what happens, let us say we are setting a distance of some L kilometers. Okay, so only when the fault is occurring anywhere in this distance, the distance relay will act. Beyond this L kilometers, if there is any fault, then this distance relay will not be giving a tripping signal. Okay, so that is the distance relay. Now the question is, how do we get a distance component into the relay? That means, how do we make distance an actuating quantity for the relay? Okay, so we know that the impedance of the line is going to be dependent on the length of the line. It will be proportional, right? Impedance will be proportional to the length. So if we can find out a relay which depends on the impedance, then you're going to get a distance relay. Okay, so this is achieved by taking the current as the operating torque, while the restraining torque is provided by a voltage coil. So in the torque equation, you're going to have the current component which will form the operating torque, and you're also going to have the voltage term, but here it is negative because it is acting as the restraining torque. Okay, now when the relay will operate, when t is greater than 0. Relay operates when t greater than 0. That means k1 I square minus k2 v square should be greater than 0. So you're going to get v by I whole square should be less than k1 by k2. Now what is v by I? It is nothing but the impedance, right? So the impedance should be less than root over k1 by k2. So if the impedance falls below this value, root over k1 by k2, then the relay will operate. Okay, so relay will operate when impedance falls below root over k1 by k2. Okay, so if you take often it is represented with the voltage and current characteristics. Okay, so if this is the V and I, what will be the impedance? Impedance will be the slope. Okay, so let us say we are taking a slope which is equal to root over k1 by k2. Now the slope, if it is less than this value, then the relay will operate. So this is called as the operation zone, and above this line it is no operation zone. That means if the slope is lying above this particular slope, then it will not operate, otherwise it will operate. This is with respect to the VI characteristics. Other most commonly used characteristics is the RX characteristics. That is, you have resistance on the X axis and reactance here, right? Now what will be the impedance? Impedance of a particular value, it will form a circle, right? So if you take Z is equal to root over k1 by k2, Z is nothing but the radius, right? The radius is given by Z. So what is going to happen? Inside the circle, if impedance falls inside the circle, then the operation will happen, the relay will operate. So this is called operation zone, inside the circle. Okay, if the impedance falls outside the circle, then it is not going to operate. It is called no operation zone, outside the circle. Okay, so because the distance relay, they operate under the basis of impedance, we also call it as the impedance relay. Okay, so distance relay or impedance relays. Further, we also have a reactance relay. This is also a type of distance relay only. Okay, but this operates on the basis of reactance rather than impedance. Okay, so what is going to happen here? The operating torque is going to be provided by the current. This is the operating torque, while the restraining torque is going to be provided by the directional unit. Okay, so minus K3 VI cos theta minus tau, here you take as, you design it to be 90 degrees. Okay, so you're going to get K1 I square minus K3 VI sin theta. Okay, so you can take, this is the operating torque, this is providing the operating torque, whereas the directional unit is providing the restraining torque. Now just like in the previous case, we can write t greater than 0 for the relay to operate, right? For relay to operate, t should be greater than 0. So this is going to give us K1 I square minus K3 VI sin theta should be greater than 0. Okay, so you're going to get here VI by I square sin theta should be less than K1 by K3. Okay, so you're going to get finally Z sin theta. This should be less than K1 by K3. Now what is Z sin theta? It is the reactance. If you take the impedance triangle, this is Z, R and X, and this is theta, right? So Z sin theta is going to give you the reactance. So X should be less than K1 by K3. Because the relay is going to operate on the basis of reactance, this is called as the reactance relay. Now if you draw the Rx curve, Rx characteristics, what will be? This is R and this is X. Okay, now a particular value of X is going to be a horizontal line. So here X is equal to K1 by K3. Now X should be less than this value for relay to operate. So what will be the operation zone? This is going to be the operation zone. Any point which is below this line, and above this line it is going to be no operation zone. Next we have a Moore relay. So here what happens, the operating torque is given by the directional unit. T is K3 V into I cos theta minus tau, and the restraining torque is provided by the voltage winding. Okay, now for the relay to operate, you can write this as well. This is the operating torque and this is the restraining torque. Now for the relay to operate, T should be greater than 0, torque should be greater than 0, right? So if you substitute the expression for torque, then you're going to get the final expression I'm writing. Z should be less than K3 by K2 cos theta minus tau, right? And what is theta here? This is the phase difference between the voltage and the current. So this expression, if you plot on the Rx graph, then it is going to give you a circle which is passing through the origin. Okay, and the operation zone will be inside the circle, and outside the circle it will be no operation zone. Impedance is calculated from the origin, right? So any point on the circle, it is going to have the value Z is equal to K3 by K2 cos theta minus tau. Okay, so if the impedance is falling inside the circle, then relay will operate. If it falls outside the circle, then it will not operate. Now one important point here in Moore relay is that it is depending on the phase angle between voltage and current, right? This is the limiting condition, and the limiting condition, you can see it is depending on the phase angle. Okay, and for this reason it has an inherent directional property. Okay, Moore relay has a directional property.